Hello everyone, we will be solving questions on statistical mechanics in this session. Okay, and I hope this will help you in your entrance exams like TIFR and all. So we're solving questions from quantum mechanics, like scattering problems and all. We'll be continuing that also. And this is a session on statistical mechanics. Okay, we'll be solving questions. The questions I will be solving will be from the book Y.K. Lim. It's a very renowned book on statistical mechanics, and I will recommend this book if you want to master the topic of statistical mechanics. Okay. Okay. So let's start solving questions. I will assume that your concepts are clear in this chapter. Okay. I had also done a lot of videos on statistical mechanics before. You can check them out in the playlist. Okay. So let's do the questions. This is the first question. Question is a classical harmonic oscillator mass. I will advise you to write the questions. They're really important. Instead of just solving the question, it's better to write the question also so that it will get imprinted in your mind. Spring constant K is known to have is known to have a total energy of E, but its starting time is completely starting time is completely unknown. Starting time is completely unknown. Okay. Find the probability density function. Find the probability density function that is Px, where Px dx, where Px dx, sorry, where Px dx is the probability. Px dx is the probability that the mass would be. Px dx is the probability that the mass would be found in the interval dx, will be found in the interval dx at x. Okay. Classical harmonic oscillator of mass m, uh, and spring constant k is known to have a total energy of E. Okay. But its starting time is completely unknown. Find the probability density function Px, where Px dx is the probability that the mass will be found in the interval dx at x. This question was asked in a university exam of MIT, Massachusetts Institute of Technology. Okay, it's the best one of the best universities in the world. Let's try this question. I would recommend you one website where MIT open course where there are a lot of courses. You can join them and they're free. Where MIT professors will be teaching you, and that will really open up your mind if you do courses here. Okay, please try. A classical harmonic oscillator of mass m and spring constant k is known to have a total energy of E, but its starting time is completely unknown. Okay. When did it start? We don't know. Find the probability density function Px, where Px dx is the probability that the mass will be found in the interval dx at x. This is the question. Some formulas will be used in this question, and I hope you know them. First of all, you have to write the Hamiltonian, the energy of the classical harmonic oscillator. came in MIT 2001. Okay, let's solve it. First of all, what is the Hamilton? What is the total energy for harmonic oscillator? Classical harmonic oscillator, we know half kx square plus half mv square, that is half mx dot square. Okay, I will write x dot, that is of dx by dt. This is actually kinetic energy. This is the potential energy term. This is the kinetic energy term. So this is a Hamiltonian total energy. Okay, half k square plus half mx dot square. Okay, we know time period is what? What is asked in the question? Probability density function Px, where Px is the probability the mass will be found in the interval dx. So probability density function Px we have to find. Okay, okay. In the interval dx. Okay. Let me find time period. Okay, probability density function. There is a formula Px dx. Okay, Px dx is equal to, there is a direct formula for it. If you can remember it, 2 dt by t. This is a formula. You have to remember it. Okay. So for that I need t. What is time period? We know time period. Very easy. Formula of time period is 2 pi root over m by k for a spring. This harmonic oscillator, right? So if I can have an expression, if I can get an expression for m, then I think I can put it. Sorry. Okay. Let me first 2 dt by 2 pi root over of m by k. So what will I do here is, um, I will I have to find an expression of m from here. Okay, then only I can do something. Mm, how can I get an expression of m? Or um, okay, this is dt by. Okay. Otherwise, we can do one thing. Um, yeah, I think it will be okay. Let me do one thing. Let me get an expression for dt. Okay, we have to get an expression for dt. Let's try to find dt, because at the end we won't need dt. Okay, I will need in, like, I need px, right? See, I need px, right? So in the left side I have px dx is equal to 2 dt by t. So if I can somehow get an expression of dt in terms of dx, something into dx, right? So I can cancel this dx on both sides. So I will get px, because I need px. I don't need px dx. I need px. Okay. So I have to get an expression of dt in terms of dx. So how will I do it? See, here in this expression, if I half kx square plus uh, half mx dot square. Okay, x dot as I have written is dx by dt. So let's put it here. So half kx square plus half m dx by dt whole square. Okay, is equal to e. So let me do it very slowly, like step by step. So e minus half kx square is equal to half m dx by dt whole square. I need dt. Okay, so 2e minus kx square divided by 2 is equal to half a mole into dx by dt whole square. Okay, so half got 2 got cancelled out in both sides. So 2e by k, 2e minus kx square divided by m is equal to dx by dt whole square. Okay, I need dt. Okay, I'm getting there. I'm getting there slowly. So root over of 2e minus kx square divided by m is equal to dx by dt. Yeah, I got it. Yeah. So dt should be what? I needed dt. So dt is what? Just it will go to that side. So m root over of 2e minus kx square dx. That's it. Yes. So I just have to put it here, right? See, we could do it. So px dx, it's not that a hard question, is equal to what? 2 dt by d. So 2 into dt is what? 2 into dt is m divided by 2e minus kx square dx divided by t is what? 2 pi root over of m by k, isn't it? So let's do one thing. Okay, mm will be cancelled out, right? 2 cancelled out, mm cancelled out, dx. Okay, wait. So root over of k, k goes off, 2e minus kx square dx. Pi is also there, na? 1 by pi. So px dx. So dx cancelled out. I needed px. So px will be what? Px is equal to 1 by pi k divided by 2a minus kx square to the power half. Okay, that's it. That's the probability density function. I hope you got it. It's a very good question. Again, solving this question will open up your mind. I'm telling you, solving the questions from this Weichelian book. It's a very good question again. Again, let me explain it. Classical harmonic oscillator mass and spring constant K is known to have a total energy E, but its starting time is completely unknown. Find the probability density function Px, where Px dx is the probability that Px dx is the probability. It's not the probability density function. Probability density function is Px. Okay, that the mass would be found in the interval dx at x. So what I first did is I wrote the Hamiltonian. Whenever you are doing statistical mechanics, you need to have a basic idea of the Hamiltonian of the system. It's always needed in case of like getting the partition function or total internal average internal energy that you do basically, or in Ising model questions. So Hamiltonian is always needed. Okay, so here also Hamiltonian. This is E energy, total energy, or Hamiltonian is equal to this, and I wrote that in terms of this the x dot square is your dx by dt and all, and at dt I put this. Okay, so I after cancellation now I got this. So this is your probability. You just have to remember this formula. Probability px dx is equal to 2 dt by t. This is a very important formula. Okay, you have to remember this. Okay, I hope you got it. If you could, if you did it, then we can move to the next question. Okay, let's move to the next question then. You can pause the video and make it also, no problem. Okay, move to the next question. Question number two. See, I have done this question before. Okay, um, should I do it or? Okay, let me do it anyway. It will be practice only. Consider a large number of consider a large number of n localized particles in an external magnetic field H. An external magnetic field H. Each particle has spin half each particular spin half. Find the number of states. Find the number of states accessible to the system. Find the number of states accessible to the system as a function of as a function of ms. ms, which is what? What is ms? Ms is the z component of. We have done this question, but anyway, I will do it again. Z component of the total spin of the system. Total spin of the system. Okay. Determine the value of ms. Determine the value of ms for which the number of states is maximum. For which the number of states is maximum. This question looks big, but it's a very easy question, and it usually comes in exams. Okay. Please try this question. You first try this question because we have done it so many times. Okay, how to solve this question? See, large number of n localized particles. So n is the total number of particles here. Okay, in an external magnetic field H. So this is the external magnetic field support. Each particle has spin half. Find the number of states accessible to the system as a function of ms. Okay, each has spin up. Okay, the thing is spin half. That means it can be plus up and it can be minus up. So it has two possible orientations. Plus up, one is spin up, one is spin down, right? One is spin up, one is spin down. Okay. So there will be like the spin plus half will be what? Will be along the direction of magnetic field. Okay. Spin half plus half will be along the direction of magnetic field. Suppose that is in one. Okay. And that is something in one, capital in one. And something that is not along the magnetic field, that is suppose n2, or it's suppose n minus n1. Okay, not we'll take as n minus n. Okay, yeah. So, so the total, like the component of the total spin, what is the component? Can you tell me? See, number of systems will be one. Number of states in this. Can you tell me? Do you remember? Do you remember how to solve this question? So this is n. This is n1. This is n minus n1. So omega is what? N factorial divided by what? N1 factorial, n minus n1 factorial, right? Hmm. And what is n1? What is n minus n1? That is again another one. Hmm. How to do it? See, find the number of states accessible to the system as a function of ms. So we have to get the answer in terms of ms. Okay. So your ms is what? Ms has an expression r whole into n, suppose n up minus n down. Okay. This is the expression for ms. Okay. So m up is what? M up is n1 minus n down is what? N minus n. Okay. So this means n1 minus n plus n. So this kind of becomes what? Half whole into 2 n1 minus n. Okay. This is our ms. So ms is what? N1 minus n by 2. Got it? N by 2. Sorry. N1 minus n by 2. So n1 is what? From here I got n1 as ms plus n by 2. N1 should be ns plus n by 2. So what is n minus n1? N minus ms plus n by 2, that is n by 2 minus ms. Got it? So 1 is, so n1 is what? N by 2 plus ms. N minus n1 is what? N by 2 minus ms. So these are the two values. We just put it here. That's it. That will be the microshades. N factorial divided by n1 factorial, n minus n1 factorial. So n factorial divided by n1 factorial is what? N by 2 plus ms factorial. This is n by 2 minus ms factorial. That is the expression. Yeah. But what is the question? Question is, okay, we got the number of states accessible. Now, what we have to find? Determine the value of ms for which number of states is maximum. So whenever something is maximum, value of ms for which number max, something is maximum. So what we do exactly? We take the derivative with respect to that, right? We take the derivative for that. Yeah. But the thing is, here, see, here the thing is, we have to take the ln of this. Okay, ln omega is equal to ln of, this is the number of matrices, n by 2 plus ms factor n by 2 minus n square. Okay. Ln omega is the number of matrices. Yeah. So again, so d ln omega by d what? D ms. Dms. What? Mm, dm. Sorry, dm is equal to 0. So because ms is maximum, so d ln omega by dn is equal to 0. So let's do it. Uh, so d by dn of ln, this one is equal to 0. Yeah, let's do it. First of all, we have to find a first expand it. Okay, because after that we can only take derivative. Let's expand it first. N factorial divided by n by 2 plus ms factorial n by 2 minus ms factorial. Okay, so this becomes ln n factorial minus ln n by 2 plus ms factorial minus ln n by 2 minus ms factorial. So this is n ln n minus Stirling formula, okay, n by 2 plus ms ln n by 2 plus ms minus minus plus n by 2 plus ms. This is minus of n by 2 minus ms ln n by 2 minus ms minus minus plus n by 2 minus ms. Okay, so minus ms cancelled out. N by 2 n by 2 is n. N by 2 n by 2 is n, and there is a minus n, so this will be cancelled. Okay, so n ln n minus n by 2 ln n by 2 plus ms minus ms ln n by 2 plus ms minus n by 2 ln n by 2 minus ms plus ms ln n by 2 minus ms. Okay, so now what? This is our ln n, ln omega. So just have to take the derivative of this one. D ln omega by dn should be what? 0. So from here you will get it. You will get your answer. The answer will be always n1 will be n by 2. This should be the answer. Always. Always it will be divided into halves like n by 2. This will be n by 2. This will be. Okay. This is plus half. This is minus. I've done so many times. I hope you understood. Just write it down so that we can move to the next question. Okay, we will move to the next question. Next question is based on a random walk model. Okay, number three. Random. There is a one-dimensional lattice. There is a one-dimensional lattice with lattice constant A. With lattice constant. With lattice constant A. As shown in the figure, an atom transits, that is moves. Okay, transits means moves. Transits from one site, transits from a site to a nearest neighbor site, nearest nearest neighbor site every tau seconds. Okay, every tau seconds. The probabilities of the probabilities of transiting the probabilities of transiting to the right and left, to the right and left, probability of transiting to the right and left are p and q is equal to 1 minus p respectively. Probability of transiting is p and q is equal to 1 minus p respectively. Okay. So this is your, so this can go here, this can go here, can go here, can go here. So this probability is p, this is your q is equal to 1 minus p. Okay. The distance between them is a. Okay. Right. So the first question is, question number, calculate the average position, calculate the average position x bar of the atom, average position x bar of the atom at the time, t is equal to n tau, at the time t is equal to n tau, where n is very greater than 1, where n is very greater than 1. B is calculate the mean square value, calculate the mean square, calculate the mean square value x minus x bar whole square bar at the time t. Calculate the average position x bar of the atom at the time t is equal to enter. Calculate the mean square value this at the time t. There is a one-dimensional lattice with lattice constant A, and an atom transits from a site to the nearest neighbor site in every tau seconds. The probabilities of transiting to the right and left are this. Calculate the average position this at the time this. Calculate the mean square value. Just try. Okay. You can pause the video and try and do this. So we have to choose the initial position as the origin. Okay, always choose. This also question came in MIT. Okay. MIT 2005. Choose the initial position always as the origin. As the origin. Okay, that is x is equal to 0 always. So that will be easy for you. So with the x axis, okay. So first of all, x bar. The formula for x bar is what? Summation n is equal to 0 to n. Okay, n factorial divided by n factorial, n minus n factorial. Okay, n minus n factorial, n minus n, a p to the power n, q to the power n minus n. So this is the formula. Okay, you have to remember this. Okay. So, what can I do from here? Calculate the average position x bar. Mm, that at t is equal to n tau. Okay, this is the initial position where x is equal to 0. Average position. Let me do one thing. Let me expand this. Summation n is 0 to n factorial by n factorial into n minus 1 n minus n factorial to n a to the power n to the power n minus n minus summation n is 0 to n factorial by n factorial n minus n factorial n a p to the power n to the power n minus n. Okay. Can do one thing. See in this one, I can do some manipulation here. Summation n is equal to 0 to n factorial by n factorial n minus n factorial to n a p n minus 1 into p. Can do that. Q n minus n minus this whole thing. Okay. So this becomes kind of 0 to n factorial divided by n factorial n minus n factorial. This becomes 2. Okay. 2ap I will take out n whole into p n minus 1. Okay. 2n minus n. So can I write minus whatever? Can I write like this 2ap del by del p of summation n 0 to n factorial by n minus n factorial p to power del by del p of p to power n is n into p to power n minus 1, right? So just did that minus whatever is it. Okay. So uh, so solving this after solving this I will get the answer. I will just try to write the answer because it's a very long derivation. It's n a 1 into p minus 2. You have to solve it. But to expand it more and more I will get this. It's very long derivation. So I'm just writing the answer na whole into p minus 2. Alright? Yeah. And this value we just have to put in the second question. There is a main square value x minus x bar whole square bar. So here x bar you have to put it here. Okay, and you will get the answer for the second one. Okay, the answer will be 4 n a square. Okay. Yeah. So, so yeah, that will be it for this class. We'll be solving more questions in the upcoming sessions. Okay. Thank you very much.